Now, our first speaker is Laya Ghodsi, that is going to talk about ALMA and WSJST, I'm sorry, on Max 1931. Please, Laya.
Okay, so hi everyone. I'm Laya Ghodsi, a PhD student at the University of British Columbia, working with Dr. Alison Mann. I'm sorry that I couldn't be there because of visa issues. But today I'm going to talk about a joint analysis of cold and warm molecular gas in circumgalactic medium in the brightest cluster galaxy of a well-known galaxy cluster called MAX 1931. This work has been done in collaboration with people at ESO, European Southern Observatory. So I think I don't need to motivate a lot why we're using CGM, why we're studying CGM, but just as a brief introduction, CGM acts as the bridge between the galaxy and its cosmological environment, and there are a lot of interactions like inflows and outflows between the CGM and the central galaxy, which can regulate the star formation of the galaxy. So CGM is multi-phase, as the title of the conference says. So we can detect CGM at different phases. In this project, we are focusing on molecular CGM. Molecular CGM again can be traced and detected using different tracers. Molecular hydrogen can be traced with CO and C1. We are using a combination of CO and C1 to trace cold molecular hydrogen because it's been shown in recent works that for some gas with specific properties, CO might be dark, and C1 is a good combination. A good combination of CO and C1 can help to trace more of the hydrogen gas. As this plot shows, the cosmic ray ionization rate as a function of hydrogen number density, you can see some places, some gas with some properties are CO dark, but C1 traceable. So in this work, we're using a combination of both to trace more molecular hydrogen with temperatures of around tens of kelvins. But we also use H2 rotational lines, which trace warmer molecular gas with temperatures around hundreds of Kelvin to thousands of Kelvin. And in this work, we have three hydrogen rotational lines, S1, S5, and S9, which I will introduce later. But our case study is the BCG of a galaxy cluster at redshift 0.35. This BCG is highly star-forming, unusual for low redshift BCGs, with a star formation rate of 250 solar masses per year, and its stellar mass is 6 times 10 to the 11 solar mass. We also see a radiolog AGN in this system, and as you can see in this composite image, in which we see the CO322 emission in red, the dust ALMA band 7 in green, and Hubble H alpha plus N2 in blue. And you can see that the tail-like structure here is extended up to 30 kiloparsec away from the central galaxy. And this whole system has one of the largest known reservoirs of molecular hydrogen with a mass of 2 times 10 to the 10 solar mass. An interesting point about this tail is that it's very gas poor. The gas to dust ratio is almost 10, which is 1 order of magnitude lower than usual value for the Milky Way. And in the lower image, you can see the profile of the emission profile of different lines, and the blue curve is showing the dust band 7 image, where you can see the tail. The dust band 7 is elevated in the tail, which is showing the tail is very dusty. And one question here is that why this tail is so dusty? Is it just unusually gas poor, or some unknown astrochemistry is going on there? One possibility is that because these observations are taken with ALMA, and ALMA is an interferometric facility, one possibility is that ALMA is missing some gas in the larger scale of this system. And that's why we used some single dish data as well as ALMA. So we detected CO726 and C1221 with APEX, and CO120 with the Nobiama single dish telescope. And And also we have some JWST data. As I said, we detected S1, S5, and S9 lines using the JWST MIRI-MRS data, and we combine these new data with archival ALMA data, which shows CO120, CO322, and CO423. So to start, it's good to take a look at the whole structure of the system. We have the BCG and the CGM extended up to 30 kiloparsec away from the BCG, and all the emission line, all the spectra show a bimodal distribution in which the larger peak is showing the emission from BCG, and a smaller peak redshifted by 300 kilometers per second is corresponded to the CGM tail. And this bimodal distribution is only seen in our C1221 new data in the upright panel. The top right panel is showing the apex data, and the top left is showing the NRO 45 meter single dish. And you can see that this bimodal distribution is obviously seen in the C1221 emission, but not in the other lines because of the limited signal to noise. And one conclusion drawn here was that the emission, the total flux from CO120 was as the same as the ALMA CO120. So showing that there is no missing flux by the ALMA observations. So there is something else going on. And this work has been published. This is the first part of my project, has been published this year. You can scan this QR code and take a look at the paper if you want. Then we looked at the CO slit. This is showing the CO slit, the line ratios normalized to CO120. And as you can see, the BCG is shown in red, CGM is shown in orange. And the BCG is on par with U lyrics, which are highly star-forming. So it's showing that the BCG is highly excited and highly star-forming on par with U lyrics, but the CGM is less excited. It's peaking at the lower CO transition, CO32. And we can also do some modeling as well as just looking at the CO slit. We can do modeling. So we use the radiative transfer code RADIX. And we used all the CO lines and one C1 line that we had in order to estimate the different properties of this gas, gas in the system. So here you are seeing the corner plot of three gas properties, the number density in the middle column, the kinetic temperature, and the visualization parameter. So this panel is clearly showing that all the black contours are showing the BCG, and all the red contours are showing the CGM. And we can see that the BCG gas is a bit hotter than the CGM. And the number density in the CGM is not that well constrained, but the peak of the number density of BCG is a bit higher than the CGM. So this plot is showing that the BCG gas, the gas inside the BCG, is hotter and denser than the gas in the CGM, which is understandable. But it's showing that the gas in these two parts of the system are different. So there might be different physics going on. That's why we looked at the JWST data. This is I'm using this nice piece of work to motivate why we are using warm molecular hydrogen. This is showing the 7th quintet, the compact group, and recently observed with JWST, published in this work of Appleton et al. In 2023. One nice thing that you can see is that the blue contours, which are showing the edge to rotational lines, are distributed mostly in the space between the galaxies, not within the galaxies. And they are tracing turbulence and shock fronts. And this nice piece of cartoon, they are showing that when a shock front is moving inside the molecular cloud, it can change the distribution of density, and the molecular clouds can be more clumpy. So we want to see if we see this this feature in our data or not. But here I'm showing our JWST data for H2S1 line on right. And this is a nice animation prepared by my friend Lucas Kuhn, another graduate student at UBC. And if you focus on here, this is the emission of BCG in the central wavelength, and then we have a redshifted tail appearing here at a more redshifted wavelength. And we see the same structure for H2S5 line. And this structure is almost the same as what we saw in the CO lines. I will talk about that later more. And we also see some more ionized lines and Paul features, which I don't have time to talk about those now. But when we compare the H2S5 and H2S1 emission with the CO322, we can see in this image the background color is showing the moment zero map of the two H2 lines. The blue contours are showing the contours on the H2 lines, and the cyan contours are showing CO322 emission lines. So we can see that the most of the BCG and the tail are co-spatial, but there is some parts of the tail which are captured in with warm, like with rotational lines of molecular hydrogen, but not with CO. So in the next step, we try to model the excitation temperature of this gas using an LT assumption, which leads us to a Boltzmann distribution for the number density of the different transition. And here you can see on the left, you can see the line ratios of the H2S5 and H2S1 line. The excitation temperature is shown in the middle, and the mass per pixel is shown on the right. So you can see that the excitation temperature for all the BCG and tail is some number around 430, but the CGM looks a bit warmer than the BCG. This still needs more work. We're still working on that, but this is some preliminary results. And the total mass of warm hydrogen in this whole system is 4.1 times 10 to the 10 solar mass, which if you calculate the ratio, the warm to cold gas mass ratio is around 0.02, so 2%, which is normal for galactic systems. And I'm going to leave you with my summary, where without this bimodal distribution in the BCG and CGM of this galaxy cluster, and the cold and warm molecular gas were co-spatial in the BCG and the tail, and the excitation temperature is around 430 for all the systems. So I'm happy to take any questions, and thank you.
Does anybody have like a quick question? Do you mind coming to listen? Because like the mic was. Can you hear the question?
Yeah, thanks for the nice talk. Maybe I missed it, but is the idea here that this tail has been stripped out of the BCG? You know, they can have relative velocities of hundreds of kilometers per second relative to the ICM. So is the idea that this stuff originated in the BCG and has been stripped out, or is it really true in situ CGM?
Yeah, well, that's a great question. We are still looking into that, but one scenario for the formation of this tail is that there has been, a long time ago, there has been an outflow from this BCG due to the aging burst, and some gas was pushed out of the galaxy into the CGM, and then after a long time, a second burst happens, and this is putting some shock fronts into this environment, and now it is condensing and going back to the galaxy. But we're still working on that. We're running some shock models to see if we can confirm that or not.
Thank you very much. Let's thank the speaker again.
Thank you.